nanohub.org.
Okay, let's continue on with our seminar, Measurement Techniques and Optimization. So, one of the questions that came up a few minutes ago was the question of settling time, and does that cause discontinuities in my data? There are several things that can impact the settling time, and most of those are controlled in what we call our timing menu. Our timing menu has access to our 3 standard speed modes, the fast, the normal, and the quiet speed modes. Just to give you a reminder of what we taught you yesterday, most people run this in the normal mode. In normal mode, it covers the broadest range of measurement situations, and it usually works very well. That's why we named it normal. In some cases, you may want the measurement to run faster, either because you want to see the transient response faster, or you just get tired of waiting for the data, and you can go to the fast mode. And in some cases, you may want to lower the noise, and so you can go to quiet mode, which will take longer, but will be more quiet. We also give you control of the sweep delay, the interval time, and the hold time, or the pre-soak time. Now, we introduced hold time yesterday in the concept of DC IV, but hold time actually becomes more important in the concept of AC impedance. In many cases, the characteristics that we're measuring on our semiconductor devices need to be preconditioned by pre-biasing the device to some condition until it reaches whatever equilibrium state that we want it to be in. And so the hold time allows us to do that. What came up earlier was the question about auto range. Now, when we auto range an AC impedance meter, what we're changing is the current measurement range, just like a current measurement range on a DC meter. And so what we have to do is we have to resettle that current range. Now, in the case of an AC impedance meter, we also have to settle the auto balance bridge, which adds some extra settling time. So what we have added for the first reading only after a range change are these default times. And these are very significant times. 400 milliseconds if you're going down to the lowest range, 200 milliseconds for the intermediate range, and 100 milliseconds for the highest range. So this is one of the penalties that you pay if you want to use an auto range on your AC impedance measurement. This is also why I recommended earlier to just choose the appropriate range and to not use auto range. This is a pretty stiff penalty to pay to allow the instrument to automatically select a range for you. Now, basically, the lower the range, the more delay time is added to settle each reading. The reason is this: a lower current range implies a higher impedance. Higher impedance implies longer RC time constants, hence more settling time. The test frequency also impacts that, in that the higher the frequency, more time is added to settle the reading, because the higher the frequency implies a higher impedance device, and that implies a higher RC time constant and more settling time. So in our timing menu, we have fast, normal, quiet, and custom. And fast, normal, and quiet are actually defined by a set of tables that we have embedded in the firmware of the instrument module itself. So we design the tables around what we call our normal tables. So the normal tables have the normal amount of settling time for the different ranges, the normal amount of A to D converter time, or shall we say signal acquisition time, in order to get the noise where we want it. And these normal times, which by the way is what our specs are written around, all right, are pre-programmed in. So if I go to a fast time, what I'm actually doing is I'm adding multiplying factors to that normal table. So if I'm on normal, I have delay factor and filter factor. Delay factor is a multiplier on the built-in normal delay, and filter factor is a noise reduction factor on the built-in normal aperture time or measurement time. So at normal, my delay factor will be 1 and my filter factor will be 1. In other words, just use the normal table, right? But if I go to quiet, I'm going to multiply the delay factor by 1.3. So that means it's going to take 30% more time to settle, or it's going to give the instrument 30% more time to settle before it makes the measurement. Now remember, the filter factor was a noise reduction factor. So basically at quiet it says, I want to reduce the noise by a factor of 3. Right? So to reduce the noise by a factor of 3, we use a simple definition of noise, and that is white noise. And white noise is proportional to the square of the aperture time. So what we have to do to reduce the noise by a factor of 3, we need 9 times more aperture time. So the aperture time is defined in the normal table. Let's use an example. Maybe I have an aperture time, the time that I actually look at the signal, of 100 milliseconds. Right? If I go to quiet mode, that will raise that aperture time by 3 squared, or 9. That would be a 900 millisecond aperture time. So just remember, delay factor is a direct multiplier on the normal settling time, and filter factor is a squared function, a noise reduction factor. Now, most users are perfectly happy with fast, normal, and quiet. But we actually give you what we call the custom time. In custom time, you can go in and specifically tune this instrument in terms of delay times and filter factors and aperture times to meet the exact need that you need. All right? Question?
Good question here. When you said the filter factor is related to the time, in a Johnson noise expression, the time is proportional, the noise voltage is proportional to the square root of the time.
That's right.
A direct relation as compared to this being inverse, when you imply that a factor of 3 means reducing it by 9?
So to repeat the question, we are now talking about Johnson noise, and in the Johnson noise equation, whether it is a Johnson noise current equation or a Johnson noise voltage equation, it is related to the square of the time. So actually there are multiple types of noise. You've got Johnson noise, you've got white noise, you've got 1 over F noise, you've got shot noise. So there's multiple types of noise, and they all have some relationship to time and to your measurement. For example, we can lower Johnson noise by increasing the bandwidth. That's your time factor in Johnson noise, right? But on 1 over F noise, as we go to lower frequency, the noise actually increases. It's a different noise phenomena. So Johnson noise is related to the square of the aperture time, or how long we look at the signal, and white noise is also related to the square of the aperture time. So that just happens to be a similar relationship on those 2 different types of noise. Okay, so here's an example of measuring a half a picofarad capacitor, 500 femtofarad capacitor, and we first measured it with the fast mode, which is this large purple curve here. And we took the same number of samples. We just sampled versus time for fast, normal, quiet, and custom. So when we ran it on fast, you see our noise is running in the neighborhood of, well, actually, I'll talk about that in the next slide. You see we have what appears to be a lot of noise on fast, but the entire curve completes very quickly. Then when we go to normal, that's the blue curve, you actually can't see it. It's buried underneath the purple curve, okay? But it takes slightly longer. You see a little bit of the blue curve here, and the noise is less. Then when we go to quiet, we get the green curve here, significantly less noise. Remember, quiet was supposed to be a 3x noise reduction from normal. right? And then we went to a full custom, which is this red curve, which stretches us all the way out here to 45 seconds. So at fast, we ran this whole curve in about 1 second. And at custom, it took 45 seconds. So it took 45 more times. 45 times more time. So the square root of 45 should have been our noise reduction factor here. What is that, roughly 7? So we should roughly have 7 times less noise. So here's the actual noise as measured by standard deviation. So when we were in the normal mode, it took 48 milliseconds per point to make this measurement. And we had 234 attofarads of standard deviation. In fast, it was only slightly faster at 39 milliseconds per point, but we had a significantly higher standard deviation. Now there's a reason for that. There's some overhead that is not directly related to the instrument aperture. So in this particular case, fast is really not that much faster, but it gives us significantly more noise. But quiet is only a little bit slower, but it's quite a bit lower in noise, only 76 attofarads of noise. And here, the custom, which took 1.5 seconds per point, is all the way down to 20 attofarads of noise on a 500 femtofarad capacitor. Now, the point here is I wanted to kind of give you a feel of the difference in time versus noise for fast, normal, quiet, and custom, and how big an impact this actually has on the measurement, both in measurement speed and in the amount of noise we can measure. I think the impact on an AC impedance meter is actually bigger than it is on a DC IV instrument. Now, just kind of a little insider tip. This particular AC impedance meter on the 4200 actually doesn't use a traditional averaging or filtering A to D converter. Basically, the way this AC impedance meter works is we continuously digitize both the voltage and the current, and we feed those digitized signals right into a discrete Fourier transform. So we are continually transforming this signal. So the longer we send this megahertz signal in, the more the noise goes down. We just keep sending it in, the noise keeps going down. Okay? So we don't have sort of the concept of averaging mode in here. Now, if you look at the way our menus are structured, they're still structured to kind of look like that because everybody's used to using averaging to reduce noise or power line cycles. But the truth is, this is a continuous aperture instrument. The longer we feed the AC signal in, the more the noise goes down. At least until we hit 1/F noise. All right, I wanted to give an example. Those were examples of very small capacitors. I want to give an example of a large capacitor. For our definition of large is 100 nanofarads. Anybody outside the semiconductor industry, 100 nanofarads is, gee whiz, can you actually even buy a capacitor that little? You know? But 100 nanofarads is large. By the way, 100 nanofarads is the last calibrated capacitance we have on our AC impedance meter. And when I say that, what I mean is our AC impedance meter is calibrated to national standards, NIST standards, Japanese standards, European standards. We have a traceable standard. We actually had to go invent a 100 nanofarad traceable standard. It didn't actually exist. So that was the biggest standard that we could get. And so that is the last calibrated measurement that we make that we can actually verify to a standard. 100 nanofarads is not the biggest capacitance we can measure. We can measure microfarads. We can measure up to hundreds of microfarads, but we just can't trace them to a standard. So at 100 nanofarads, we see our normal curve is the blue one here, and our fast curve is the red one, and our quiet curve is this purple one. So you see the blue takes about twice as long as the red, all right? And it has significantly less noise. But you have to be aware of the scale. We're on 100 nanofarad full scale, but we're only moving from 0.05 nanofarads per division. We're only moving 50 picofarads per division. So we only have a few hundred picofarads of noise at fast on this 100 nanofarad scale. Again, I see this happen all the time. Because the graph in this instrument is auto-scaling, if you have it set up to do that, oftentimes we will see it take a really low noise measurement but blow it way up on the scale, and if you visually look at it you go, why is that measurement so noisy? Well, it's not noisy, it's just the scale. The scale bites people all the time on this instrument, so be aware of that. Oh, we actually have the numbers here. So at fast it took 100 readings in 1.1 second, and that gave us a 8.6 picofarad standard deviation. Normal took twice as long, and it gave us a 2.8 picofarad. And quiet took a full 10 seconds for 100 readings. That's 100 milliseconds per reading, and that gave us 1.4 picofarads of standard deviation. So what is that? About 11 milliseconds per reading, I think, on that one, if I calculate that right. Yeah, 2 digits down. So 11 milliseconds per reading to measure with 8 picofarads of standard deviation, that's a pretty fast measurement. Now this instrument, it's sort of its best case is about, I think I've got it down to about 5 milliseconds per point. That's about as fast as it can process an AC impedance measurement, is 5 milliseconds a point. So if you were to do any transient testing, like a test that we used to do in the old days was deep level trapped spectroscopy, where we would pulse the device into a state and then watch the capacitance recover. In many cases at room temperature, we needed to see recoveries in hundreds of microseconds. This instrument won't do that. But a lot of times at Kelvin, at cryogenic temperatures, you know, you can easily see the device recoveries at 5 millisecond acquisitions. All right, this is actually on a MOSFET, on a wafer. This is actually a really big MOSFET, 4.6 picofarads of gate capacitance. All right, and so I just wanted to give an example on an actual wafer of fast, normal, and quiet. And that doesn't have a chart of the noise. So we actually have the standard deviations here. So our best standard deviation is about 84 attofarads on a 5 picofarad capacitor. That's 6 digits of resolution on a wafer, on a MOSFET, on a gate. So this is sort of a real world environment that you can experience. This is not, you know, some Cal standard that we have plugged on the back of the instrument. So now, how do we choose the appropriate hold and sweep delay times? All right. This is very important, and it's very important because in the semiconductor world, many of the things, the parameters that we're trying to extract are time-dependent parameters. They're things that change with time, and we detect those changes by looking at a change in capacitance or conductance. So we need to know what the appropriate times are. You know, the condition of a device when all capacitances are fully charged after a change in voltage is called equilibrium. Right? If capacitance measurements are made before the device is in equilibrium, we're making it in an undetermined state. Now, sometimes I actually want to chart the change in capacitance as I'm reaching equilibrium. That tells me something about what's going on in the device. Sometimes I want to make sure the device is in equilibrium because I'm looking for some other effect. So to choose the delay times on a CV sweep, what we usually do is we put a step function of voltage and we watch the capacitance recover. When the capacitance stops recovering, that amount of time is what it took for that device to reach equilibrium in that condition. So to choose the delay time, step the voltage using the sampling mode. I usually use initial conditions of 0 hold time, 0 interval, and 0 pre-soak voltage. In other words, I want to take capacitance as fast as I can. Plot the capacitance as a function of time and observe the settling time, and then use this as a hold time. In other words, this is how long you have to apply voltage to your sample before you even begin testing it. Here's an example of an equilibrium measurement on a device. In fact, I don't even know what this device is, but clearly when this device responds to a step function, it takes it over 10 seconds to reach a state of equilibrium. So when we step functioned this device and measured the capacitance, it took this device 10 seconds to fully respond to that step function. So if we were interested in measuring this device in an equilibrium condition, we know initially it takes at least 10 seconds for this device to reach equilibrium. Now, if you're measuring MOS capacitors, and we use standard silicon dioxide MOS capacitors for our examples. For one thing, they're very well understood. So if you want to determine equilibrium on your MOS capacitor, and this is important if you're, for example, doing doping profile, you need to make all your measurements under equilibrium conditions. You have to allow time for the MOS capacitor to reach equilibrium condition, both sufficient hold time and sampling time. That's the time between measurements. So there's two primary indicators that we use to determine whether the device has reached equilibrium. One, you check the shape of the CV curve. Two, you look at the hysteresis of the CV curve. So here's an example of a hysteresis curve. Now, hysteresis for this definition is what we call a dual sweep. That's where we sweep the CV curve from some starting to some ending voltage and sweep it back again. And a MOSFET actually will respond to hysteresis. If he's not in equilibrium, he'll respond differently in the two directions. So we swept from here in the forward direction and got the forward curve, but when we reversed it, the curve jumped up and came back again. So this hysteresis here tells us that we actually weren't measuring this MOSFET in equilibrium. Now, if this device were in equilibrium, it would always sit right on this perfect equilibrium line. Now, in the case of interface trap analysis, which is something that we've talked about a little earlier, you need to make some assumptions about equilibrium. Otherwise, it becomes almost impossible to deconvolve the signal that's interface traps from the signal that's just charges moving around in your device. Here's another example. This actually came directly off the 4200. You can tell because I have the little Keithley banner on the graph. Right? So this device, we swept it fast, and the device wound up coming down into what we call the deep depletion region. If it had been in equilibrium, we would have gotten this curve. Now, a common trick in MOS devices is to sweep them backwards, to sweep them from the inversion region to the accumulation region. However, if you don't give them enough hold time in the inversion region to build up an inversion region, you will get something like this. It will sweep backwards, and then at some point it will snap up to the equilibrium curve and continue on. So the old trick for doing this is to bias it to inversion and give it a shot of light, and that will actually drive it to inversion, to equilibrium, and then you can run your sweep. This is one way to determine the equilibrium time of a MOS cap. Just bias the thing in a step function down to inversion. It actually drives it to deep depletion, and then watch it recover from deep depletion up to inversion capacitance. This particular device took 20 seconds to generate enough carriers to go from deep depletion to inversion. Now, if I hit this with something that would cause it to generate carriers, like a flash of light, a lot of times that will jump this immediately up, and then I can begin making my measurements in an equilibrium condition. So let's talk about reducing the effects of stray capacitance on our measurement. We have what we call offset connection compensation. This goes by a lot of different words. I've heard it called cable calibration, cable compensation, or just calibration. Really, I try to reserve the word calibration for meaning something that I'm calibrating the instrument to a known national standard. Everything else, I try to call it connection compensation. Okay. For a multi-frequency auto-balance bridge AC impedance meter, we normally use two corrections, what we call an open correction and a short correction. Open correction corrects for large impedances, which are normally small capacitances, and short correction corrects for low impedances, which are big capacitances. We also have a concept of guarding on an AC impedance meter, which is similar but different in its implementation than the guarding that we talked about for a DC meter. And then we also are going to talk about the proper connections of the ammeter terminal of the CVU. So the CVU, remember, has a high terminal and a low terminal. Well, in the case of a CVU, the low terminal is normally the ammeter terminal, and that terminal can be sensitive to where you connect it to the sample. So here's sort of a graphic representing what we're doing when we do open and short correction. If we had an ideal capacitor plotted, well, let's plot it here. If we had an ideal capacitor here, in other words, that capacitor truly is 1 picofarad or 10 or 100 picofarads, right? And then we measured it, and this was our measured result. We are going to come up with some error. In other words, if I could measure perfectly, my 1 picofarad capacitor would be 1 picofarad or 10 or 100 or a nanofarad. But I'm going to have some offset errors and some gain errors. All right. So the offset errors that I get down here low on the scale are normally caused by, or normally corrected by, the open compensation. The offset errors that I get high on the scale are compensated by the short compensation. Now, we actually have a webinar online called CV Tips, Tricks, and Traps, where we actually go in and present the models for this. So if you're interested, you can go to the Keithley website and go online, look for that webinar, and it gives you the full models on this. So here's how we actually implement open and short correction in the 4200. It's a two-part process. We have a specific menu that you access from the Tools menu. This is the main screen in Kite. It has a Tools menu at the top, and it's called CV Correction Compensation. And that opens up the correction compensation menu, where I can do a measure open, measure short, and actually measure load. And it will go out and it will prompt you what to do, and then it will make the measurements, and then it will populate correction tables, which, if you're really a measurement geek like me, you can go in and see what the correction coefficients are if you choose to do that. Okay. Yes?
Traditionally, we have been ignoring the load correction.
Right.
We don't have a 50 ohm load per se to factor in, and we just do the open and short corrections and dual measurements. What do we do in this case? Can we ignore it? And what's the cost of ignoring it, or how do we do it otherwise?
That's a very good question. Let me repeat the question. So the question was, traditionally, we ignore this third parameter, the load correction, because it's very difficult to have a known load that I can put out there. And the answer is that's the correct thing to do. So we only added, in our case, this load correction capability because it's in there in a traditional LCR meter. It's actually a very specialized correction that only works within that narrow region of the load. Maybe it's a 50 ohm load or a 50 picofarad load. Okay, and it only works there. It's only for bringing that narrow point right into as close an accuracy as we can get. What we find in the semiconductor arena, the open correction actually does 90% of what we want a correction to do. Right? The short correction adds a little more to it. Open correction does small capacitors or high impedances. Short correction does big capacitors. We usually don't see big capacitors in the semiconductor arena. So open and short correction are all you need to do. In fact, load correction often will work against you because it will shift the curve for regions outside of that particular load. So, we put it in there for traditional reasons. I've never used it. I don't use it at all. Thanks for that question.
Just one more follow-up. I take it these corrections are frequency specific, is that correct?
Okay, let me repeat the question. So the question was, I take it these corrections are done at different frequencies. So that brings up a design philosophy that Keithley followed on this particular AC impedance meter. This is a multi-frequency AC impedance meter, and it's actually driven by full digital and DSP techniques. So we can actually digitally generate any frequency that we want. We can generate, if we wanted to, multiple frequencies at once. We chose not to. We chose in our range of 1 kilohertz to 10 megahertz to do 10 points per decade. In other words, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 kilohertz, 20, 30, 40, 50 kilohertz, etc. We chose 10 points per decade. We chose that for a reason. That allows us to do 100% frequency calibration at the factory. We calibrate every frequency in every range. And it allows us to do 100% frequency and range open and short correction. So every frequency and every range in the Keithley, when you click measure open or measure short, it does every frequency and every range. And it creates a table for that. Now, if you look at a traditional LCR meter, which might have thousands of frequencies per decade, it actually goes in and corrects only 5 or 6 or 10 per decade, and then interpolates the rest of them. And we actually have some examples of, over the years where we saw interpolation errors in the measurement. So we chose to go 10 frequencies. Our research showed, in general, 99% of the time, that's more than enough frequencies for everybody, but it gives us 100% correction capability. Now, it takes, I'm trying to remember, I'm thinking it takes 30 seconds to run a measurement open. So when you click the measurement open button, it takes about 30 seconds to run every frequency and every range that we have. That's about what it takes. I can't remember for sure. All right, there's another sort of important point here, and that is what we call our default cable length. Now, AC impedance meters are measuring AC amplitude and phase relationship between the voltage and the current. So phase is an incredibly important part of this measurement. But we get a phase shift as we go down a cable. A standard coaxial cable is running probably in the neighborhood of 55% of the propagation delay in vacuum. In other words, it takes a certain amount of time to get down that cable. Even if we were projecting through vacuum, we can only move at propagate a wave at a certain speed. But down a cable, it's only 55%. Keithley's cables actually were specially designed to give us about, I think we're running 70% propagation velocity down our cables. But the point is this, it creates a phase shift in the cable. So we have what's called a cable length term. All right. And in this particular menu, it sets up what we call the default cable length. It shows here 3 meters. Actually, the default cable length is 1.5 meters. That's what comes with the instrument. The default cable length is the length that's automatically pre-programmed in when you build a new test. So if you go and you grab an empty test, a new ITM, and you go to build a CV curve, it will pre-program in 1.5 meters for you. This is just the default cable length. You have the option of changing that cable length later. When you're actually in the test itself, if you actually have a different cable length, you can go in and change that cable length. So cable length is actually an important correction. Open and short don't completely compensate for the phase issues that we see going down a cable.
So is the correction length specific or not?
Say again?
The corrections, the open and short,
yes.
Are they length specific, or we correct and then we can start measurements and change cable length subsequently?
So if you do open and short and then change the cable length, it will change your results. So open and short really are, they're not completely independent, but you can view them as being independent of the cable length. So when you do the open and short here, you don't need to set cable length before you do that. I think that maybe that's your question. So open and short operate independent of cable length. Cable length is not important before the open and short. The models that I generate in my other webinar will show you why that is. But cable length is very important when you actually make the measurement. Actually, now that I think about it, this is actually the last generation of software. We've actually added a new button and a new feature here called custom cable length. This is a really cool thing. I've got to tell you about this. So what we said was, you know, a lot of people will be hooking these into probe stations, you know, and we can't predict exactly what all the manipulators and the cables and things are going to be. Or maybe they'll run it through a switch matrix, and we can't predict what the path length is going to be. So what we came up with, because we have a fully digital instrument, we actually came up with a way of measuring the cable length. And so what we actually do is we take and we generate and send a pulse down what we call the current terminal or the force terminal, and that pulse goes all the way down, comes back the sense terminal, and is sensed back with our sense voltmeter. Because we know the timing precisely when we made the pulse versus when we measured it, we can measure the entire time of the round trip. If we make a assumption, and this is assumption that we require of you, that it's equal distant on the force and sense terminals, in other words, you've got matched path lengths or matched cables, then we can divide it in two, and we know how long it took us to get down to the end of the cable. So we actually measure the phase change or the prop delay down to the end. So if you look at a traditional LCR meter, and if you look at the way we implemented initially, we're basically saying, I'm assuming that you're using the proper cable and that it has a propagation velocity that I know, and therefore if you tell me the length, I know what the phase change is down the cable. What we found is that isn't true. People use whatever cable they have laying around. They hook it up and you know, we don't know what the propagation velocity is on that. So, you know, we strongly recommend you use Keithley's red cables. One of the reasons is it matches our prop velocity that we're expecting. Also, it's a very high performance cable. It's got a faster prop velocity, so there's less error there, or more, I should say there's more predictability in the error. Okay, but our new method, our new button says, well, I'm going to go out there and calculate it for you. So now, as it turns out, at say a megahertz and down, at a megahertz, propagation velocity is starting to become an issue. Okay, above a megahertz, it just gets worse and worse and worse. As you get to 10 megahertz, propagation velocity or delay is really starting to become a significant factor. Okay. All right, so we did a standard test on a MOSFET. By the way, this is a high-frequency CV curve. I know it looks like a quasi-static curve, but it's a high-frequency curve because what we did is we tied the drain, source, and substrate together. So we gave the gate to channel capacitance a source of minority carriers that can respond as fast as the AC signal. And so we start accumulation, we sweep through depletion, and we come back to inversion, right? And we did this with no corrections turned on. I don't know if I got my test settings in here. I didn't put the test settings in. This is probably done in a megahertz. So it's at about 4.5 picofarads, 4.65 picofarads, and here's our curve, all right? Then we took the device, this was in a test fixture. We took the device out of the test fixture, but we left the test fixture connected, and we did the open correction. We went into the menu, did the open correction, turned it on, and ran it again. And this is our new curve with the open correction. The result was our entire cabling system and test fixture, in this case we were just using the red cable, so it's just the test fixture, gave us in the neighborhood of 170 femtofarads of offset on a 5 picofarad capacitor. Now, we had a question yesterday when we were trying to do a simultaneous CV. We're doing high frequency and quasi-static, and what we had was a shift in the curves here in accumulation, which was pretty significant. So in simultaneous CV, what we're doing is we're comparing high frequency and quasi-static and saying this shift in the curve, actually in this region of the curve, is due to interface traps. But as you can see here, just because I didn't measure high frequency correctly to begin with, I actually have 170 femtofarads. This device would, if I were doing that technique, would show me I've got probably 10 to the 11th or 10 to the 12th interface traps in this device. It's all just measurement error. So it points out how important on the high frequency curve the open and short correction is. So this is an example on a low impedance or 100 nanofarad capacitor. So this blue curve is with no short and no open correction. The red curve is with the open correction. Notice it didn't change. Remember, on a low impedance, our open correction in our model is really not having an impact. But look what changed when we actually did the short correction. So when we do an open and a short correction, we compensate across the entire spectrum of the AC impedance that we plan to be measuring. And what this does is it gives you some confidence that really no matter what I'm measuring, the results are probably going to be right.